Hello, in this lecture, we are going to continue with the series on basic real analysis, and today's topic would be series, that is infinite series. Okay, so having done some little bit of sequences, we are starting with series, although I like to mention that we are going to continue with sequences in parallel uh, as and when required. So don't worry about it. So we are going to do both of these topics, that is sequence and series, now in parallel. Okay, so given a sequence, this is how I can write that given a sequence an of real numbers of real numbers, a formal sum, a formal sum of the form summation n equals to 1 to infinity an is called an infinite series. It is called an infinite series. Now for any n belongs to natural Sn, which is defined by a1 plus a2 dash 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 an, it is called as a sequence of partial sum. It is called as the sequence of partial sum. So basically, if you have an infinite series, let us say if I'm saying that summation n equals to 1 to infinity represents your infinite series, so this is this way, it will go on. Or you can write it as limit n tends to infinity Sn. And what is Sn? Sn is the sequence of partial sum. So in series, we'll say that the series summation n equals to 1 to infinity an is convergent if the sequence of partial sum associated with it, that is if Sn is convergent. In such case, the limiting value of Sn is called as the sum of the series. Okay, so understand again, and reiterating on this fact because this is one of the most important fact. That is, if I'm saying that I'm considering a series, that is, let's say k equals to 1 to infinity ak, it would imply what? It would imply a1 plus a2 plus a3 dash 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 an dash dash dash. Basically, it is equal to writing limit n tends to infinity Sn, where Sn is the sequence of partial sum. Now, as n tends to infinity, it will go along and it will become the same this way. So if I want to see the convergence and divergence of series, I need to concentrate on sequence of partial sum. Understand, this is not a1, a2. Sequence of partial sum would be what? If I'm saying S1, it would be a1. If I'm saying S2, it would be a1 plus a2. If I'm saying S3, it would be a1 plus a2 plus a3. If I'm saying S4, it would be a1 plus a2 plus a3 plus a4. So this is what it is going to be. Okay, so a series behaves the same way as its SOPS does. So if the series is convergent, then SOPS is convergent. If SOPS is convergent, then series is convergent. Or if series is divergent, then SOPS is divergent. And if SOPS is divergent, then series is divergent. SOPS means sequence of partial sum. This is one thing. Some important series I'm going to write which are convergent in nature. One of them is geometric series. So if I write a series of the form A plus AR plus AR square dash 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 ARN, then this series is convergent provided mod R is less than. So this is a convergent series. Another series which I want to mention is telescopic series. Now, what is a telescopic series? So let AN and BN let an and bn be two sequences. Such that an is given by bn plus 1 minus of bn plus 1 minus of bn. And we note that S1 would be simply equals to A1. So let's say I'm saying that let Sn be equals to the partial sum of An. So this is how I'm defining. Now S1 would be simply equal to A1. S2 would be simply equals to A1 plus A2. Okay, and what is A1? A1 would be B2 minus B. What would be S2? S2 would be A1 plus A2, and it would be equals to B2 minus B1 plus B3 minus B2. So here you can see this cancel out, and you'll get B3 minus of B1. And if so on, you're going to do, if I'm writing Sn, now Sn would be simply equals to A1 plus A2 dash 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 An, which would certainly give you B2 minus B1 plus B3 minus B2, and at the end you are going to get Bn plus 1 minus of Bn. Now, if you just see the cutting pattern, you can observe that the only surviving term would be Bn plus 1, sorry, Bn, because in every bracket, the latter part, for a latter part, you have a former part. Okay, so eventually this would get cancelled. You will be left with Bn plus 1 because this is former. It requires a latter part in the next bracket. So this would survive and this would survive. So this particular sum, or this, you can say the limit Sn would exist, or in other words, summation An would exist only if limit, in fact, if and only if limit Bn exist. Okay, and precisely in that particular case, summation An would be equals to limit Bn minus of B. So this is how we work with the telescopic series. Let us do a few questions to understand how to work with the telescopic series. So just take one question and then let us try to do it. So let us try to find what would be sum of n equals to 1 to infinity n upon n raised to power 4 plus n square plus 1. We want to find this. Okay. From our elementary algebra, we know that n to power 4 plus n square plus 1 can be written as n square plus n plus 1 times n square minus n plus 1. So if I want to manipulate with the numerator part, I can write the numerator part as simply this 1 upon 2, and I can here write n square plus n plus 1 minus n square minus n plus 1, and then you have this bracket n raised to power 4 plus n square plus 1. Now this entire thing would be 1 upon 2. Sums n equals to 1 to infinity. This would be simply 1 upon n square minus n plus 1 minus 1 upon n square plus n plus 1. Okay. Now, if I solve this up, what I'll get? If I solve this up, that is sums n equals to 1 to infinity n upon n raised to power 4 minus n square plus 1, I will get simply 1 upon 2. Let me place n equal to 1. So it would be simply 1 here, minus, if I place 1 here, it would be simply 1 by 3. Plus, if I place n equals to 2, this is 4, minus 2 is 2, plus 1, this is 1 by 3. If I place 2 here, so it is 2 square 4, 4 plus 2, 6, 6 plus 1, 7. Again, if I place 3 here, this is 1 upon 7. And if I place 3 here, it is 3 square is 9, 9 plus 4 is 13. And this is how it is going to be. And let me just write a term before and then one more term. So basically, if I just write one more term here, so this would be n minus 1 whole square. I'm just trying to expand it, let's say till k, and then I'll take limit k tends to infinity. That would be a better thing to do. So k minus 1, here it would be minus of k minus 1 plus 1 minus 1 upon k minus 1 whole square plus k minus 1 plus 1, and at the end the last bracket would be, I'm just writing it here, the last bracket would be plus 1 upon k square minus k plus 1, and then plus 1 upon minus, sorry, k square plus k plus 1. Okay, so this is one thing. Now you just think about all these things. So basically how these what just note the cutting pattern. This is 1 upon 2, minus 1 upon 3 cancels 1 upon 3, minus 1 upon 7 cancels 1 upon 7, minus 1 upon 13 cancels. So in any bracket, the latter part is being cut by the next bracket's former part. In any bracket, the latter part is being cut by the next bracket's former part. So in any bracket, the latter part is being cut by the next bracket's former part. You Okay, you can see this. So if you just want to write it, it would be k square minus 2k plus k. This would be minus k plus 1 minus 1 would be 1. This is equals to this one. So in any bracket, this latter part does not have a former part. So this will survive anyway. Okay. So basically, now you are left with only 2 points. That is 1 minus 1 upon k square plus k plus 1. And also you should understand there is a limit running over k tending to infinity. So answer should be half. So answer of this particular very complicated looking series would be simply half. So this is how telescopic series works. So basically in telescopic series, you need to work this way only, the way I told you already. Okay, so this is one. Now let us do a few more questions so that we are quite acquainted to this telescopic series, and then we'll see all the more conditions in the next lecture. So today let us focus more on the telescopic series and how to work with telescopic series. Okay, try to find me the sum of, I mean, this is not even, right. Try to find the sum of the series. So how would one do this? See, if I want to find the sum of this series, how would I do it? I would simply try to do this. I'll simply write k equals to 1 to n, and I'll take n tends to infinity here, and I will simply write it as 1 upon 4k square minus 1. And then I will simply write it as limit n tends to infinity, sums k equals to 1 to n, and then I will write 2k minus of 1 minus 1 upon 2k plus of 1, and I know there is 1 by 2 here, so I'll balance it using 1 by 2. So basically summation n equals to 1 to infinity 1 upon 4n square is nothing but it is equivalent to finding the limit n tends to infinity summation k equals to 1 to n, half is here 1 upon 2k minus 1 minus 1 upon 2k plus 1. Okay, and this is equivalent to writing limit n tending to infinity. Now let us write this. Let us try to solve this. Place 1 here. So this would be 1. Place 1 here. It would be 3. Place 2 here, it would be 3. Here it is 3. And place 2 here, it would be 1 by 5. Place 3 here, it would be 1 by 5. Place 3 here, it would be 1 by 7. And dash dash dash, the last term would be 2n minus 1 minus 1 upon 2n plus 1. So basically now, if this is the case, 1 by 3 cancels 1 by 3, 1 by 5 cancels 1 by 5, my 1 by 7 cancels 1 by 7. So in any bracket, the latter part, except this one, in any bracket, the latter part is being cut by the next bracket's former part. So in any bracket, the latter part is being cut by the next bracket former part. So this particular bracket, in this particular bracket, this would survive because there is no such former part of the next bracket. And here this is a former part to this bracket, so therefore it corresponds, it will get cut by some latter part of the previous bracket. So basically what I will end up getting, I'll end up getting n equal to 1 to infinity, 1 upon 4n square minus 1 is simply equals to 1 upon 2, 1 minus 1 upon 2n plus 1. Limiting value n tends to infinity, this will go to 0, so value would be 1 upon 2. I hope this is clear to you. Just pay attention to these questions. Such questions are very easy and they may be asked in your examination also. I hope it is clear. Now let us try to do a few more. Just try to do this. This is an easy question. Try to do this. Try to find the sum n equals to 1 to infinite tan inverse of 2 upon n square. If I want to find this sum. So this would be equal to finding limit k tending to infinity, n tending to infinity, summation k equals to 1 to n tan inverse of 2 upon k square. Now you see there's a formula where you have this tan inverse of x minus y upon 1 plus xy, and if you want to write this as here it is minus and here it is I think plus. Okay, so if this is equals to tan inverse of x plus minus tan inverse of y. So anyway, this formula requires 1 here. So what I'll do, I'll do some manipulation and that will help me in this assessment of the limit. So what I'll do, I'll simply write tan inverse of 2 instead of 2, I'll just write 2 here and I'll write 1 here and then I'll subtract 1, which implies limiting value n tending to infinity sums k equals to 1 to n, and this is equals to tan inverse of k plus 1 minus k minus 1. So basically 2 can be written this way, and this is 1 plus k plus 1 times k minus 1. Okay. Now so basically don't forget that we are finding tan inverse of 2 upon n square, n equals to 1 to infinity, which is equivalent to writing limit n tending to infinity sums k equals to 1 to n tan inverse of this entire thing, that is k plus 1 minus. So basically this would be tan inverse of k plus 1 minus of tan inverse of k minus 1. Okay, this is one thing. And if I want to evaluate this, let me just try to write the values now. Place 1, so this would be tan inverse of 2. Place 1, so this will be tan inverse of 0. Okay, place 2, this would be tan inverse of 3. Place 2, it will be tan inverse of 1. Again, place 3, this will be tan inverse 4 minus tan inverse 3. Again, place, I think this is 4, tan inverse of 5 minus tan inverse of 3. And we'll go along. Let me just write, last bracket would be tan inverse of n plus 1 minus tan inverse of n minus 1. Just place another bracket here. Instead of k, you just place n minus 1. Again, place another bracket n minus 2 here. So this would be and so on and so forth. So now just observe the cutting pattern. Importance is observing the cutting pattern with all patients. Otherwise, you'll make a mistake. Tan inverse 0 is 0. Just don't worry about it. Tan inverse 2 would survive because this is tan inverse 3, I guess. Now, in any bracket, the former part is being cut by the next bracket's latter part. Okay, this is one thing that you can see. No, this is tan inverse 2, I guess. Just see it. I think if I place 3 here, so this is, sorry. This is 2. Sorry. So in any bracket, in any bracket, the former part is being cut by the next to next bracket's latter part. Okay, this is how the cutting pattern is. In any bracket, the former part is being cut by next to next bracket's latter part. So in any bracket, the tan inverse 4 would be cut by next bracket's latter part. If you just think, what is tan inverse 5? So the next bracket would be what? Next bracket would be tan inverse of 6 minus tan inverse of 4. Clearly, the former part of a bracket is being cut by next bracket's latter part. So tan inverse 1 would survive anyway. Tan inverse 0 is 0. Forget about it. Now, in any bracket, the former part is being cut by next bracket latter part. So this is former. It does not have a latter here. It is also former. It does not have a latter here. So this would survive. This would survive. This is a latter part. So it will get cut by former part of this bracket, and this would be cut by the former part of some bracket. So basically, what you can think is that there would be only a few things left. So I'll write n equals to 1 to infinity tan inverse of 2 upon n square. Limit n tending to infinity. There is tan inverse of n which is surviving. Then there is tan inverse of n plus 1 which is surviving. And then there is minus of pi upon 4 which is surviving because this tan inverse 1 is pi by 4. So just think about it, that this would be equivalent to writing pi minus of pi over 4, which is simply 3 pi over 4. So sum of this difficult looking series is simply 3 pi by 4. Okay, so now let us try to do one more question on this pattern only so that you get used to this particular pattern. So the next question that comes in the line is again a question in tan inverse only. Let me just frame it for you. Just try to do this. Summation n equals to 1 to infinity tan inverse of 1 upon n square plus n plus 1. So how would you do it? So simply I'll do one thing. I'll simply write it as n equals to 1 to infinity tan inverse of 1 upon 1 plus n square plus n. What is it? What is the good part about this is writing this is, see, what I'll do this, I'll write this as this, that is n equals to 1 to infinity tan inverse of 1 upon 1 plus n square plus n. I can write this as limiting value limiting value n tends to infinity, summation k equals to 1 to n, and this is simply tan inverse of 1 upon 1 plus k square plus k, and which is equivalent to writing limit n tending to infinity, summation k equals to 1 to n, and this is simply that this k 1 can be written as k plus 1 minus of k. Okay, and this can be written as k plus 1 into k. So I think it's quite evident that I can write this way. Okay, now if I want to write this, if I want to find this, which is summation n equals to 1 to infinity tan inverse of 1 upon n square plus n plus 1. So this is equivalent to writing limit n tending to infinity summation k equals to 1 to n. Now, if I just start writing the values, if I just start writing the values, I mean, if I just start placing the values, sorry, what I will get? I will simply get, just place 1 here. So this will be tan inverse 2 minus place 1 here. So this will be tan inverse 1. Place 2 here. This will be tan inverse 3. Place 2 here. This will be tan inverse of 2. Place 3 here. This will be tan inverse of 4. Place 3 here. Minus tan inverse of 3. And dash, dash, dash. You'll get place n minus 1 here. So this will be n. Place n minus 1 here. It could be n minus 1. Place n here. Tan inverse of n plus 1. And place this is how it is. Now you see, if I just start striking off things, so basically in any bracket, the latter part is being cut by the next bracket's former part. So this is surviving, forget about it. So in any bracket, the former part is being cut by the next bracket's latter part. In any bracket, the former part is being cut by the next bracket's latter part. In any bracket, the former part is being cut by the next bracket's latter part. So only thing I guess is surviving is this tan inverse n plus 1, which would be pi by 2 as n tends to infinity. And this tan inverse 1 would be simply pi by 4. So I'll write pi by 4 here. So answer should be pi upon 4. I hope this. Let's try to find one more sum, which is given by k equals to 1 to infinity tan inverse of 8n divided by n square n to the power 4 minus 2n square plus 5. So in order to find this, what I'll do, I'll simply do one thing. This is limit n tending to infinity summation k equals to 1 to n. This is tan inverse of 8k divided by n raised to power 4 minus 2n square plus 5. So one of the ways to do this question would be to manipulate with this denominator. So what I'll do, I'll simply take this in two parts. See, just understand. So I'll write 4 separately, and inside I have this. I'm so sorry to write this. Okay. So this would be k raised to power 4 minus 2k square plus 1. And here you have this 8k. Try to divide 4 throughout. So you'll get limit n tending to infinity. This is summation k equals to 1 to n. This is tan inverse of what is 8k? 8k would be simply, if I take this 4, if I just divide, this would be 2k, which would be equals to k square, sorry, k minus 1 whole square minus, sorry, k plus 1 whole square minus k minus 1 whole square divided by 2. So this will give me, if I divide it by 4, so I'll get 2k, 2k is this, fine. And this is 1. And this entire thing, this is k square minus 2k square plus 1. This is simply k plus 1 whole square. So this is what? So just understand, this is k plus k square minus 1 whole square. So which can be written as k plus 1 whole square and k. So basically what I'll write k plus 1 whole square divided by 2 into k minus 1 whole square divided by 2. So overall, I get to know that the sum I'm interested in would be equivalent to writing limit n tending to infinity summation k equals to 1 to n tan inverse of k plus 1 whole square by 2 minus tan inverse of k minus 1 whole square by 2. If I want to find it, what I will get? I will simply get limit n tending to infinity. Try to place 1 here, so you will get tan inverse of 2 square upon 2 place 1 here, I'll get tan inverse of 1 square by 2. Try placing 2 here, this will be tan inverse of 3 square by 2 minus, try placing 2 here, this will be tan inverse 1 square by 2. I think this would be 0 because see, tan, if I just place 1 here, so 1 would be tan inverse 2 square by 2, this would be 1, so this is 0. If I place 2, this would be tan inverse 3 square upon 2. Okay. Then if I place 3, it would be tan inverse of 4 square upon 2 and tan inverse of 2 square upon 2. And similarly, if I go all along, I'll get tan inverse of, if I place n minus 2 here, so I'll get n minus 1 whole square divided by 2. If I place n minus 2 here, so I'll get tan inverse of n minus 3 whole square upon 2. If I place n minus 1 here, I will simply get tan inverse of n square upon 2. And if I place n here, now if I just try to calculate this, just see this thing. See, in any bracket, the former part is being cut by the next brackets, next to next brackets latter part. In any bracket, the former part is cut by next to next brackets latter part. Okay, so all these would get cancelled. See, in any bracket, the former part is being cut by next to next brackets latter part. So what would be surviving? This will be surviving 1. This would be surviving 2. And this is also surviving right now. Okay, so overall you see that there are terms like pi, because as n tends to infinity, this would be pi by 2, this would be pi by 2, this is simply pi minus of tan inverse of half, which I can simply write it as pi by 2 plus pi by 2 minus of tan inverse of half, which I can write it as cot inverse of half. And again, cot inverse of half can be written as tan inverse 2. So this is pi by 2 plus tan inverse 2. So I hope you are able to use manipulation in order to find the sum of the series. From tomorrow onwards, we are going to see some tests and how to claim about the convergence and divergence of the series. Till then, take care. Bye-bye.